Hello students, this is Usha from G.K.Jain High Secondary School. Today we are going to learn the optics parts 8 in 12th standard physics. In this we are going to learn about the diffraction. So the bending of the waves at the edges are called diffraction. So we learn about Fresnel diffraction and Fraunhofer diffraction. 12th standard physics optics part 8. So now we start with diffraction. Diffraction is bending of waves around sharp edges into the geometrically shadowed region. Light should travel in straight line in a medium without bending, but the diffraction is prominent only when the size of the obstacle is comparable to the wavelength of the light. This is the reason why sound waves get diffracted prominently by obstacles like doors, windows, etc. The wavelength of sound wave is large and comparable to the geometry of this obstacle. We learn about Fresnel and Fraunhofer diffraction. Now we'll talk about the Fresnel diffraction. They have spherical or cylindrical wavefront undergo diffraction. Light wave is from a source at finite distance. For laboratory condition, convex lenses need to be used. It is difficult to observe and analyze. Whereas in Fraunhofer diffraction, plane wavefront undergo diffraction. Light wave is from a source at infinity. In laboratory conditions, convex lenses are to be used, easy to observe and analyze. Next we'll go for diffraction at single slit. Let a parallel beam of light fall normally on a single slit AB of width. The diffracted beam falls on the screen kept at a distance. Let C be the center of the slit. The line perpendicular to the point C and meet on the screen at O. Right? We would like to find the intensity at the point P on the screen. The line joining P to the different point on the slit can be treated as parallel lines, making an angle theta with the normal CO. All the waves start from parallel to each other from different point of the slit and interfere at the point P and other point to give the resultant intensity. So we know to find out the condition for the point P to be various minimas. The basic idea is to divide the slit into much smaller even numbers of parts. Then add their contribution at P with the proper path difference to show the destructive interference takes place at the point to make it minimum. So now we'll divide them into equal parts. Condition for P to be first minimum. Consider the slit AB into two halves AC and CB. Now the width of AC is A by 2. So the path difference of light wave from the different corresponding points meeting at point P and interfere destructive to make it first minimum. The path difference delta between waves from the corresponding point is delta is equal to A by sin theta. The condition for the P to be first minimum, that is A by 2 sin theta is equal to lambda by 2. Denominator 2 will be get cancelled, so we'll get A sin theta equal to lambda, that is the first minimum. Then condition for the P to be second minimum. Let us divide the slit AB into 4 equal parts. Now the width of each part is A by 4. The path difference delta between waves from these corresponding points is delta is equal to A by 4 sin theta. The condition for P to be second minimum, that is A by 4 sin theta is equal to lambda by 2. By simplifying we'll get A sin theta is equal to 2 lambda, the second minimum. In the same way we can go in for the third minimum. The slit is divided into 6 equal parts. Then we'll get A sin theta equal to 3 lambda. Now condition for P to be nth order minimum. Divide the slit into 2n number of equal parts. Make the light produced by one of the corresponding point to be cancelled by its counterpart. Then the condition for the nth order minimum is A by 2n sin theta is equal to lambda by 2. Simplifying we'll get A sin theta equal to n lambda, that is for the nth minimum. Next we'll go in for the condition for maximum. For points of maxima, the slit is to be divided into odd number of equal parts so that one part remain uncancelled, making the point P appear bright. The condition for first maximum is A by 3 sin theta is equal to lambda by 2 or A sin theta equal to 3 lambda by 2. The condition for second maximum is A by 5 sin theta equal to lambda by 2 or A sin theta equal to 5 lambda by 2. The condition for third maximum is A by 7 sin theta is equal to lambda by 2 or A sin theta equal to 7 lambda by 2. In the same way, condition for the nth maximum is A sin theta is equal to 2n plus 1 into lambda by 2. That is for the nth maximum, where n equal to 0, 1, 2, 3, etc. is the order of diffracted maximum. The central maximum is called 0th order maximum. The point of the maximum intensity lies nearly midway between the successive minimas. Discussion on first minimum. Let us consider the condition for first minimum with n equal to 1. So we'll get A sin theta is equal to lambda. The first minimum has an angular spread of sin theta equal to lambda by A. Now we have special cases to discuss on the above condition. When A is less than lambda, the diffraction is not possible because sin theta can never be greater than 1. When A is greater than or equal to lambda, the diffraction is possible. Here two conditions are given. For A is equal to lambda, sin theta value is 1, which shows that theta equal to 90 degree. That is, the first minimum is at 90 degree. The central maximum spread fully into the geometrically shadowed region, leading to bending of the diffracted line to 90 degree. If A is very much greater than lambda, then sin theta value is very much less than 1. The first minimum will fall within the width of the slit itself. The diffraction will not be noticed at all when A is greater than lambda. And also comparable, say A is equal to 2 lambda, we'll get sin theta is equal to 1 by 2. Then theta equal to 30 degree. They are practical cases where diffraction could be observed effectively. Next, we'll go into difference between interference and diffraction. First is interference. Interference is superposition of two waves. What is diffraction? Bending of waves around edges. Interference, superposition of waves from two coherent sources. They are equally spaced fringes. Intensity of all the bright fringes is almost same. Large number of fringes are obtained. These are the points for the interference. About the diffraction, bending of waves around edges happen. Superposition wavefront emitted from various points of the same wavefront. Unequally spaced fringes happen here. Intensity falls rapidly from higher orders. Less number of fringes are also obtained. These are the points for the diffraction. Next, we'll go in for diffraction in grating. So the grating has multiple slits with equal width of size comparable to the wavelength of the different light. Grating is a plain sheet of transparent material on which opaque rulings are made with a fine diamond pointer. This is available in our lab. With using this, we have an experiment also. When you come to your lab, you can see that. The modern commercial grating contains about 6,000 lines per centimeter. The ruling act as obstacles having a definite width B, and the transparent plate between the ruling act as a slit of width A. The combined width of the ruling and a slit is called grating element, that is E is equal to A plus B. Points on successive slit separated by a distance equal to the grating element are called corresponding point. So the diagram is shown over here. So a plane transmission grating is represented by AB. Let a plane wavefront of monochromatic light with wavelength lambda be incident normally on the grating. So the slit size is comparable to that of the wavelength the incident light diffracted at the grating. Now the diffracted pattern is obtained on the screen when the diffracted waves are focused on the screen using a convex lens. Let us consider a point P at an angle theta with the normal drawn from the center of the grating to the screen. The path difference delta between the diffracted wave from one pair of corresponding points is delta is equal to A plus B sin theta. This path difference is the same for any pair of corresponding point. The point P will be the bright when delta is equal to m lambda, where m is equal to 0, 1 to 3, etc. Combining the above two equations, we get A plus B sin theta is equal to m lambda, where m is called order of diffraction. Now, conditions for 0th order maximum m equal to 0, that is A plus B sin theta equal to 0, which shows that theta equal to 0, then sin 0 will be equal to 0, and m is also 0. This is called 0 order diffraction or central maximum. Condition for first order maximum m equal to 1, then A plus B sin theta 1 is equal to lambda. The diffracted light meet at an angle theta 1 to the incident direction, and the first order maximum is obtained. In the same way, for the second order, we can do condition for the higher order the central maxima of different higher order of diffracted maximum are formed at different angular positions. Then we can take n is equal to 1 by a plus b. Then n gives the number of grating element or ruling drawn per unit width of the grating. The number n is specified on the grating itself. Now the equations become 1 by n sin theta is equal to m lambda, and sin theta is equal to n m lambda. This is the formula. Then experiment to determine the wavelength of monochromatic light. So this is in the lab we can do the experiment, the grating experiment. The wavelength of the spectral line can be very accurately determined with the help of the diffraction grating and a spectrometer. For initially, the spectrometer adjustments has to be done. The slit is collimated is illuminated by a monochromatic light whose wavelength is to be determined. The telescope is brought in line with the collimator to view the image of the slit. The given plane transmission grating is then mounted on the prism table with its plane perpendicular to the incident beam of light coming from the collimator. The telescope is turned to one side until the first order diffraction image of the slit coincides with the vertical crosswire of the eyepiece. The reading of the position of the telescope is noted. Similarly, the first order diffraction image on the other side is made to coincide and their readings is also noted. The difference between two positions give 2 theta. Half of its value will be given as your diffracted angle for first order maximum. Then the wavelength of the light is calculated from the equation lambda is equal to sin theta by nm, where n is the number of rolling per meter in the grating and small m is the order of the diffracted image. In the same way, we are able to find out for the different colors also by using a white light. So next is resolution. The effect of diffraction has an adverse impact in the image formation by the optical instruments such as microscope and telescope. For a single rectangular slit, the half angle theta suspended by the spread of central maxima is given by the relation sin theta is equal to lambda. When a circular aperture or opening, that is like a lens or the iris of our eye, forms an image of one point object, the image formed will not be a point but a diffraction pattern of concentric circle that become fainter while moving away from the center. They are known as iris disk. So this is shown in the diagram. The circle of central maximum has the half angular spread given by the equation. Right? Then a sin theta is equal to 1.22 lambda. Here the numerical value 1.22 comes from central maximum found by circular apertures. This involves higher level mathematics which is we discussed in the other chapters. For small angle, sin theta is equal to theta, so a theta is equal to 1.22 lambda. Rewriting will get theta is equal to 1.22 lambda divided by a, and R0 divided by F is equal to 1.22 lambda by A. Then we get R0 is equal to 1.22 lambda F divided by A. Then we have here, you can see the pictures. When 2 point sources close to each other form image on the screen, then diffraction pattern of one point source can overlap with another and produces a blurred image that is shown in the first diagram. Then to get a good image of the two sources, the 2 point sources must be resolved. That is, the point source must be imaged in such a way that their image are sufficient far apart from the diffraction pattern to not overlap. According to Rayleigh's criterion, for 2 point object to be just resolved, the minimum distance between these diffraction image must be in such a way that the central maximum of one coincide with the first minimum of the other, and vice versa, that is given in the second diagram. Such an image is said to be just resolved image of the object. The Rayleigh's criterion is said to be the limit of resolution. So, when the distance between the two maxima is at least or not, then angular resolution has an unit in radian, and it is given by the equation theta is equal to 1.22 lambda divided by A. It shows that the first order diffraction angle must be small as possible for greater resolution. The inverse of resolution is called resolving power. This implies the smaller the resolution, the greater is the resolving power of the instrument. The ability of an optical instrument to separate or distinguish small or closely adjacent objects throughout the image formation is said to be resolving power of the instrument. Students, you all have learned about the diffraction. We'll meet you in the next video. Thank you.